All right, so we're going to look at inverse functions, and as a precursor to actually telling you what those are, we need to have one other item defined, and that is what a one-to-one function is. A function is one-to-one when each y value has assigned to it only one x value. From a graphical standpoint, one way to determine that is with the horizontal line test. We had a different line test. What was it called? The vertical line test. The vertical line test said that if I drop vertical lines and it never crosses more than once, it's a function. The horizontal line test is a very similar statement. If I draw horizontal lines across and it never crosses more than once, then it's one-to-one. And if you can imagine, like a graph that's a parabola, if I draw vertical lines, I'm good, right? Only crosses once every time. No problem with vertical lines. But what happens if I draw horizontal lines? What's happening? Crossing at 2 points, at least in many cases, right? Not in every single case. There is this point down here at the bottom. I didn't draw it well. Let me try that again. This point at the bottom where it barely just touches, that vertex point once. But many of my lines cross twice. So this graph would be considered not one-to-one. Now, we talked about a relationship last time that has this feel to it. We talked about functions, and I talked about like a mother-child relationship. Every child has exactly one biological mother, right? So it makes it a function, but if you switched it around, it didn't work. Just because you're a mother doesn't mean you have only one biological child, okay? So in that scenario, that would not be a one-to-one relationship. You can't just say, got the mother, I know exactly which child goes with that mother. I know exactly which mother goes with that. It doesn't work both ways, right? However, one of the scenarios that we could describe, at least from an evangelical Christian point of view, is that if you have a married couple, one husband equals one wife. That's the relationship that we describe, right? So that's that one-to-one that we're talking about. So we're not talking about polygamy or something like that. That would be a function relationship that's one-to-one. When we're looking at graphs on lines, we can use the horizontal line test, and it's really straightforward because we're drawing those horizontal lines. So if you take a look at these graphs, visually, we should be able to decide if they're one-to-one. Is number one one-to-one? Yes, it is. Every horizontal line I draw crosses once. How about on number 2? No. Every time I draw a horizontal line, I'm crossing multiple times, right? 1, 2, 3, 4, lots of times. And if the graph keeps going up and down, even more. We've seen graphs too where they're just a bunch of ordered pairs, right? Just a series of dots or points. And I have to be able to draw horizontal lines that only cross once. Kind of my important values are at every point. So if you take a look at that collection of points, is it one-to-one? Yes, it is. Every horizontal line that I draw that crosses will cross only once. Right? I hit all my points specifically, but you have the idea, yeah?
So, like, this how it is, like, 0, this is what time it crosses.
Say again, Preston, I'm sorry.
Would it
Okay, but the dots are my only ordered pairs. Do you see the blue dots? Yeah. So the origin itself is just 1 point, and when I draw a line through it, it only crosses through that 1 point. There's no other points plotted that are on that same horizontal line. If there were, like let's say I did have a blue dot over here, then it would fail to be 1 to 1, and we would say no, it's not. All right, so why does it matter? Well, it matters because we want to talk about inverses. And inverses are relationships that change everything back. So if you talk about or think about driving from your home to college, wherever your parents live, if you were driving, there's one direction you could get there, and you could go backwards, right, in the exact same way you did. You go through all the same roads, all the same stoplights, whatever, and that would be an inverse relationship. If you do both, if you come to school and then you go home, you have repeated everything backwards. That's what an inverse relationship is. But it only works when we have functions that are 1 to 1. I can only repeat things backwards if I already have functions that are 1 to 1. So I'd like to talk then about inverse functions. We saw an example of this from your homework last time. There's actually a couple of them in there. You guys talked about one of them as a homework question. 1-to-1 functions, f and g, would be considered inverse functions if f composed g of x is x and g composed f of x is x. So if we can do the composition of these two functions, whatever they are, I end up back where I started. I started with x, I ended up at x. I started at home, I ended up back at home. There is a notation for an inverse function. I didn't think to put it on the slide, but it's going to come up here in a moment. The notation for this looks like a superscript, like an exponent. It's not an exponent, but it looks like it, of -1. And this is read as f inverse. And if it had an x down next to it, you say f inverse of x. Okay, so it's not read as f to the -1. It's not f -1. It's f inverse. Anytime we see that -1 exponent looking thing, it means inverse. Awesome. So if this is the relationship that has to exist, we should be able to test whether it exists if I'm given two functions. And that's where we're going to begin. We're going to take two functions. F of x is x plus 7 over 2. And g of x is 2x plus 7. Sometimes it's easy to tell when functions are inverses of each other, and sometimes it's not as easy. But we can always test whether they work by finding these compositions. So we're going to find f of g of x, and if it works, then we'll find g of f of x. Okay, if it fails already, there's no reason to keep going. We know the answer will be no. So we did this last time. And you guys asked some good questions at the beginning of how to do these again. Right now it says that g of x is inside, so I'm going to replace it with what g of x is equal to, which is 2x plus 7. And then this notation says to replace x with 2x plus 7. And to do so in the f of x function. So I have 2x plus 7, and then it says plus 7 over 2. And we simplify. What is 2x plus 7 plus 7 on top? 2x plus 14. And what would 2x plus 14 divided by 2 be? X plus 7. Now, I mean, it is x plus 7, and that's fine. But what I really care about is whether or not it's x, and this isn't, right? This does not equal x at the end by itself. It has to equal x all alone by itself. And if it doesn't, then f and g are not inverses. Now, it's worth noting that you might be able to look at this and say, but if I made one little change, it would have worked. Can you see what that little change would have been where I would have gotten an x at the end? Can anybody see it? How would I ended up with not the plus 14 on top? Okay, the problem would have been here, right? What I circled in red, what could it, if it had been something different, what would it have had to have been to get rid of the value on top instead of add 7 to it? Who said it? -7. Is that what you said too, Jack? Yeah. -7. If this had said -7, right, subtracting 7 instead of adding 7, I would have had 2x on top only, right? This piece wouldn't have been here. 2x divided by 2 would have been 2. It would have worked, okay? And that's valuable information, but again, it's only helpful if somebody sort of proposes to you what the f and the g might be to start with, right? That's asking for quite a bit of information to start with and not generating it from scratch. So we are going to, not the next example, but in a moment, start with a function and find its inverse. But before we do, I'd like to take a look at an ordered pair example. So there's that notation that I brought up, right? What does this mean again? It's the inverse. It means h inverse. And here's my function h up here. I'll give you a chance to write it down, and then we'll talk about what this notation says that's different from before. Are we good to chat? Okay, so normally you have questions that we have had recently, questions that looked like this. It said h of 7, and they're telling you that x is equal to 7, find y. Right? That's what that notation means. X is equal to 7, find y. When I have inverse notation, it flips it all around. If I have h inverse of 7, it means y is equal to 7. Find x. Right? It's backwards. That's how I started by describing this. You come from school or home to school, you go from school back to home, you go backwards. So all the notation is flipped. So this question over here says that y is 6, and they want you to find x. So which ordered pair, the first one, the second one, the third one, the fourth one, or the fifth one is valuable information to this question? Yeah, the second one. In the second one, I actually have 6 in the y spot. So what would the x value be there? -1. If I'm doing the same sort of thing on part B, h inverse of 4, what would I get? Somebody said 7. That's right. Over here, h inverse of 4 is y. The x value that corresponds is 7. And I hope you can see with this example, especially with numbers, why it has to be 1-to-1 for this to work. If I had another ordered pair that looked like this on this list, there would be 2 x values assigned to that y value, right? And I wouldn't be able to answer the question with a single value. What is h inverse of 4? Well, it's 7 and it's 3. Well, that's not good. The relationship is supposed to be 1-to-1. I put in one question, I get out one answer. And that's why this is what's not allowed. The functions have to be 1-to-1 for them to work. So let's talk about how we actually find inverses when we do have 1-to-1 functions. I mentioned we switch everything. Everything is backwards. So the first thing that you do is you switch x and y. All the x's become y, all the y's become x's. Now, I realize that this says f of x because many of our functions say f of x equals instead of y equals, but it's interchangeable for y. X becomes y becomes x. Once we do that, we solve for y. And our final answer is to rewrite our notation with an inverse in it instead of it saying y equals. It's just a notational step. Okay, and the next 3 examples, I think it was 3, are finding these with different types of functions. Everybody good? All right, here's our first function, g of x. G of x is negative 2x plus 9, and we're going to look and find g inverse. So the first thing I do is what? What was step 1? Yep, switch g of x, which means y, to say what? Okay, it right now, I mean, I know it doesn't, but it really does. This is really just y already. So I change it to x. And I change my x to y. Okay, so step 1 is just switching x and y. X's become y's and y's become x's. And remember, g of x is just another way of saying y. So that's why it changed down into x. All right, what was the second step? Solve for y. So first thing I would do is subtract my 9. So I have x minus 9 equals negative 2y. And then what would I do? I would divide by negative 2. So my y equals x minus 9 over negative 2. And what's the last thing I have to do? Yeah, rewrite it in the inverse notation. So instead of y, it will say our function's name, which was g inverse. It's not a very exciting step at the end. It's just mirroring the notation from the beginning. However the notation started, I use the inverse notation at the end. And hopefully when you look back, you can see some semblance of why that would make sense. Do you see how one of them is multiplied by negative 2 and the other one's divided by negative 2? And how one of them has a positive 9 and the other one has a negative 9? Yeah, and that's what happens when we look back and compare from where we began to where we ended. Linear functions are pretty straightforward, so let's do one that's not linear. The next one's a square root function. So, first thing to do is to rewrite my function, right? The f of x becomes x, and the x becomes y. Is everyone good with that? So if I'm solving this for y, what would I need to do next? We work from the outside in. We would subtract 7 to begin with. So the first thing we have is x minus 7 equals the square root of y minus 4. Then we would need to square both sides. So I'm going to leave it as x minus 7 squared, at least for now. And I'll have y minus 4 on the right. Then what? What was the next one? Add 4, right. And please do not add the 4 to the 7. That 7 inside is underneath a square. Don't add those together. This is x minus 7 squared plus 4 equals y. That's a parabola, and you should know how to graph that. It's a parabola shifted how? To the right, 7, and up 4. Okay, cool. And then what's our last step then to rewrite this in proper notation at the end? That's not what I mean. You could do that, and I'm okay if you do. I'm okay with you leaving it like this as well. But I was talking about the rewriting of the y. How could y be rewritten to mirror the notation that began with it, that we begin with? F inverse, yeah. So F inverse of x, and it will equal 7, or x minus 7 squared plus 4. Okay, and if you, again, compare these pieces, here I have a square root, here I have a square, here I have a minus 4, here I have a plus 4, here I have a plus 7, here a minus 7. Everything has an equal and opposite reaction to it, right? Yeah, it's compensated for when we undo things. The domain here is very interesting because if you look at this function, it looks like a parabola, and you know that parabolas can have any input, right? Parabolas do this. But please tell me what's wrong with this parabola when we're talking about inverses. It is not a one-to-one function. Very good, Keely. I can't have a whole parabola. I must have just part of it. It's the only way that's possible. Because if I eliminate half the parabola, then I'm one-to-one, right? I don't have the other half of what's going on. So what's the deal? Well, the deal comes in back up here. Up here, if I were to graph this, and you know how it graphs, it's shifted right 4 and up 7, right? Right 4 and up 7. So graphically speaking, it would have looked like this. To start with. Half a parabola on its side. We've talked about that, right? What are my range values? What are my y values here? Well, climbing up the y-axis, where do I first see y values? At 7. And then they keep going after that, right? I mean, they look like they're going very flat, but they keep going up forever. So my range is actually -7, excuse me, to infinity. When it asks me for the domain down here, if x and y are switching, which is exactly what's happening, x and y switch, then so do domain and range. The domain of f inverse is equivalent to the range of f. And the range of f was 7 to infinity. And you can only know that if you go back and look at where you began. All right. I'm going to skip the next one, but I'll post it online and you can watch it. I want to show you one more that has a graph. Okay? This one's uniquely different. We have this graph, and we're asked to find the graph of the inverse, and there are no equations to work with. But one of the things that I've said all along is that the whole point is that we're reversing things, and as we do the algebra, we reverse x's and y's, right? X becomes y, y becomes x. It's a role reversal when we invert things. So what does that look like graphically? Well, it's actually pretty cool. Graphically, when we do an inverse, it is a reflection over, y equal x. So what do I mean by y equal x? Well, y equals x is a line. It's this line, in fact. And you guys know how to do reflections. We've reflected over the x-axis, we've reflected over the y-axis. Well, this is a sketch of a reflection over the y equals x axis. I meant to get a line there. So it would look something like, well, almost like a kite when we're done. Actually, let me do it ordered pair, it'll make it easier. This point right here is the point -3, 3. And if I switch that and I do 3, -3, I just switch x and y, that's my other ordered pair. And this point at the end is -5, -3. And if I do -3, -5, I just switch x and y, then I have the other pair here. Okay, x's and y switch, and they switch from a graphical standpoint as well. Okay, so I'm going to stop this video. I'm going to re-record a very short video. It'll be less than 5 minutes of the one question that is just a little bit different. It's this one right here. And if you take a look at it, the reason you might think that it looks different is 2 reasons. Number 1, there's a fraction. I didn't do one with a fraction already. And number 2, there are 2 locations where you see x. Does everybody see that? There's an x on top and an x on bottom. So I'll show you how you deal with that in a second video that I'll post.